Hi, welcome to Hands-on ARCore Development. This is section 2, ARCore In-Depth. Now, in this section, we're going to talk about motion tracking, environmental understanding, light estimation, user interaction, and anchoring objects. This video is about motion tracking, and in this video, we're going to talk about concurrent odometry and mapping, feature points, and pose, position and orientation. These are the fundamentals behind how ARCore works. So what is concurrent odometry? Concurrent odometry is basically a way for a mobile phone to know where it is relative to the world around it. ARCore uses the poses, which was mentioned earlier as position and orientation, to understand where a phone is relative to the world around it. So ARCore detects visually distinct features in the captured camera image called feature points and uses these points to compute its change in location. The visual information is combined with inertial measurements from the device's IMU sensor to estimate the position and orientation of the camera relative to the world over time. So visual odometry is an area of research that a lot of researchers have developed interest in over the past few decades. Odometry itself is the use of data from movement of actuators to estimate change in position over time in a device. In this case, when we say actuators, we're talking about inertial motion sensors in a device like accelerometer, magnetometers, and so on. So visual odometry is the process of determining equivalent odometry information using sequential camera images to estimate distance traveled. Visual odometry allows for enhanced environmental understanding in ARCore-enabled devices. So concurrent odometry and mapping takes cues from visual odometry to create a new system for generating mapping in an environment. So ARCore is based specifically on concurrent odometry and mapping, which is a method for an electronic device to track its motion in an environment while building a three-dimensional visual representation of the environment that is now used to correct drift in the tracked motion. So the COM system behind ARCore includes three major modules. The first is the motion tracking module, the mapping module, and the localization module. So let's start with the motion tracking module. The front-end motion tracking module is configured to receive visual sensor data from the imaging cameras from the mobile phones and depth data from the depth sensor at the back of the phone and inertial sensor data from the non-image sensor. The front-end motion tracking module also generates estimated poses, which is position and orientations from the received sensor data, and generates feature descriptors corresponding to the visual appearance of spatial features of objects in the environment. So just to paraphrase, feature descriptors are things that find objects in the environment that is being captured by the camera and allow you to recognize them as distinct features. So next is the mapping module. The mapping module builds a three-dimensional visual representation of the environment based on a stored plurality of maps and feature descriptors and estimated device poses received from the motion tracking module. The mapping module also provides the three-dimensional visual representation of the environment to a localization module, which identifies correspondences between stored and observed feature descriptors. Now, let's talk about the localization module. The localization module is basically a module that performs a loop closure, minimizing the discrepancies between matching feature descriptors to compute a localized pose. The localization module optimizes the three-dimensional representation and estimated current pose by solving a co-optimization algorithm that treats previously generated 3D points as variables. So the localization module basically corrects drifts in the estimated current post to generate a localized post and sends the localized post to the front-end motion tracking module for output to the API. So feature points, like I mentioned earlier, in general computer vision research, feature points or descriptors or image descriptors are descriptions of visual features of the contents in images, videos, or algorithms or applications that produce such descriptors. They basically describe elementary characteristics such as the shape, the color, the texture, or the motion, among others, of features being shown in a screen or being manipulated. ARCore understands the environment by looking at collective feature points lying on a single horizontal surface. Feature points are basically visually distinct features in an image the camera captures. So pose, which is position and orientation in ARCore, represents an immutable rigid transformation from one coordinate space to another. Pose describes the transformation from object local coordinate space to the world coordinate space. And for those who don't have experience with 3D or game programming or 3D image modeling, to explain some of these terms, a transformation is basically defined using a quaternion rotation about the origin followed by a translation. So a unit quaternion, also known as versor, provides a convenient mathematical notation for representing the orientation and rotation of objects in 3D dimensions. A translation by a vector refers to the movement of one or more points of a space in a particular direction by a specified amount. Now, a translation of a pose is the position vector from the destination, which is usually the world space, to the local coordinate frame expressed in the destination's coordinates. So we're going to talk more about that later and explain it like in layman language. But to kind of give a sort of mathematical view or geometrical view, let's talk about world coordinate space. And before we talk about world coordinate space, let's talk about what is the space in itself. In an abstract sense, a geometrical space, for example, an Euclidean space, is a boundless extent where objects tend to exist. The space defines basic properties that objects existing in this space should satisfy. So, as ARCore's understanding of the environment changes, it adjusts its model of the world to keep things consistent. When this happens, the numerical location or coordinates of the camera and anchors can change significantly to maintain appropriate relative positions of the physical locations they represent. So this means that every frame should be considered to be in a completely different world coordinate space. The numerical coordinates of anchors and the camera should never be used outside the rendering frame during which they were retrieved. So when we're talking about anchors here, we're talking about points that you use to signify specific features in the frame, which we're going to talk about more in the next video. So in this video, we basically introduced you to concurrent odometry and mapping and the modules that makes it work, which is the fundamental concept on which ARCore is based. So it's important to know what's going on behind the scene because it gives you a better view when you're developing applications.